Oh, hi there. We're glad you're watching one of our virtual lunch presentations. We have a lot of good information that we've been accumulating over the past several years, and we invite you to look down just below here and hit the subscribe button, and the little bell will give you a reminder of when our next presentation is published here on the YouTube channel. Thanks for your support. Appreciate it. A topic that we looked at last year. And Ray Lewis has kindly offered to bring us some slides this time and discuss what it means to be on a shared site. Uh, for some stations, all they think about is the fact that they're saving money by going on a shared site and not operating their own, or they can think about the options where there's one fellow who's watching over all the stations in case there's a problem. But you can find some liabilities, some issues. And Ray, as we turn this over to you, tell us about the joys and the pains of living on a shared site.
Yeah. Good afternoon, everyone. I've enjoyed working with you guys past few years and learned a lot. You guys have a lot more knowledge. I was into broadcasting when I was in college and grad school. I worked at Channel 5 in Atlanta, and that's how I paid for all of my schooling and really enjoyed it. And you get broadcasting in your blood, and you can't get it back out. So me and my wife, started we started this little LPFM, I guess almost 10 years ago now. Really enjoyed that. And but day job is doing antenna work for it used to be Scientific Atlanta, and now it's called ViaSat. And get to work on a lot of high-powered stuff. But I'll say, unfortunately, I'm having more problems with people on site having a lot of interference issues, especially with the new 5G transmitters. We'll talk about that quite a bit. I just kind of wanted to talk about what you can do, how you can assess this issue. It can actually be pretty complicated, and we've got sites on all over the world right now that are having problems, especially with 5G. And it's not that they're transmitting inside of our satellite bands; it's that they're close to the satellite band with multiple carriers, and it's creating intermodulation that we're all very familiar with. So there's all kind of stories about that. But yeah, we're doing up to 24-meter reflectors, and I don't know, up to almost 100 kilowatts of average power. A lot of high power antennas, and have a lot of fun. I don't have to tell you how crowded the environment is now. So if you go somewhere, let's see, I think Barry was telling me in California, his key fob doesn't even work at his automobile anymore. There's so much high power on Mount Wilson now that things are getting kind of crazy, which I guess isn't too much of a problem unless you're having to receive an STL signal, for instance, or something else. And we've got a lot of options now for licensed and non-licensed services now. But it's the 5G, I'm telling you, the past year is just really causing a lot of havoc, and we can talk about that. I won't go over this in too much detail. You guys all know this, but for digital communications, you've got to have a certain bandwidth and a certain carrier to noise ratio with Shannon's law to get the theoretical channel capacity. So that's the problem is this carrier to noise ratio is limited by the local interference. What that does is that makes the antenna noise temperature increase artificially. So you can do a G over T budget, which is similar to a carrier to noise ratio. And if you've got this external interference coming in, theoretically, you may have something that, will close the link quite well with a low bit error rate. But when you get on site, and especially as they keep adding more and more transmitters, that's a big problem. So we're dealing with that all over the world right now, and we're adding filters, and it's really, I was shocked the first time we were having interference in the band, because some of the satellite downlinks, some of them aren't shared, and the only thing you can legally use them for is downlink. And I was ready to call the FCC. Then we found out we have local intermodulation issues going on outside. So everybody knows the stories of those. we'll talk about amplifier overload. This is a big deal now because if you have a receive subsystem with a low noise amplifier, um, your link budget generally will look at the signal coming in from your, say, your station, your studio, and you may be in the linear region with that, but you get all these other signals in concert with that. It's going to add up and possibly drive these amplifier subsystems into saturation, and that's going to cause a lot of problems. And it's even the amplifiers after the LNA. Sometimes we have a post amplifier, and we often have a receiver of some type, and you can drive that into saturation too. So it's something that you really need to do a budget. You need to take the aggregate of all the local interference. We always do something called a site survey. Um, Usually it's done about a year in advance, and we have to send somebody out in the field with a broadband antenna and a spectrum analyzer, and they try to sample all the local interference, the EMI. We use that to generate custom filters for each one of these earth stations. But unfortunately, what we're seeing is we do this 6 months to a year in advance, and by the time we get things on site and get it up, it's changed. It's gotten worse. So we're seeing that become a big problem. And if you're trying to track a missile or launch a satellite, these are high stakes things, and people get pretty excited about that because there's a lot of money on the line. There's a lot of local simple things. I'm sure you guys have all seen this. I have had a site in Europe, actually above the Arctic Circle, and it seems like every 10 years they get a flexure in their hard line. If the flexure is between the high power amplifier and the diplexer, which is basically a low pass filter in this case, this will radiate. And if you're radiating amplifier energy, high power energy, it's basically white noise in the receive band. That's going to get in directly into your antenna. So we see a lot of real simple things like this. This actually happened for a second time, I guess, in 10 years. I was actually over there 10 years ago. We fixed it, and apparently it's such an extreme environment, so cold, and they do get some flexure that this happened again. So things like that can be a problem. Of course, we get solar effects from the sun. We've had a lot of sunspots recently, and terrain. Anytime you start looking at the ground, we call that a lookup angle, or what am I trying to say? The obscura angle. We have a obscura angle at each site, and it shows the lookup angle to the terrain in a 360-degree azimuth. So we also have adjacent co-channel stations. You can pick those up from the side lobes. So if you can reduce your side lobe level from the antennas, that's a good thing. And as we all know, there's a lot of non-coordinated systems out there too, especially in the 900 megahertz region. And I guess last is intentional jamming, which I guess is pretty rare. This is interesting. This is part of the Deep Space Network. The 70 meter, this one's down in Canberra, Australia. We have one at Goldstone, we have in Madrid. And this is antenna that I did a few years ago. And this is a 10-meter reflector. This is not a small antenna, really. And it's the same size as the subreflector on the 70 meter. But you can see how they typically put these things in a bowl. And the reason is they're trying to keep out the terrestrial interference, because this is what they use for bringing in data from the deep space probes that they have. So antenna noise temperature is a big deal. These are cryogenically cooled amplifiers, and they spare no expense when it comes to the signal to noise ratio, because there's just not much to be had with the probes that are now outside our solar system. So it's interesting. This is a big deal. People use this quite a bit. Like I said, we've got 3 of these systems around the world now. But you have to be careful with these other systems too, to make sure that what we're transmitting is clean. And anyway, another thing is the geosynchronous arc interference. I think before we used to have like 10-degree spacing, and now it's down to 2-degree spacing. So you can have multiple satellites in the geosynchronous arc. And if the side lobe level of your antenna, your Earth receive antenna, has enough energy, it will pick up the co-channel frequency from a different satellite too. So that's another consternation that we have with interference. And there's actually a side lobe mask for the transmit and the receive. Basically, it's like 29 minus 25 log theta side lobe mask that we have that the Earth station antenna has to conform to before it has a license to transmit into the geosynchronous arc, because we don't want to. What we don't want to do is we don't want to talk to a satellite, say in this position right here. Maybe that's 113 degrees west, and then over here at 116 degrees west, there's another satellite over here, and we would start to interfere with that. So I think most of the systems guys would agree that we're interference limited now instead of signal to noise rate limited. Now, so this is another source of interference. These are some of the new GSM frequencies. There's more than this now, but you can see we have a lot of these frequencies. We have this cell site just across the street from where I'm located now in Duluth, Georgia, and it transmits 40 or 50 watts, I believe, total power. So a lot of interfering signals, and they're being added to. As you all know, we lost a lot of our C-band to 5G recently. Instead of going from 3.4 up to, was it 4.2? I think we just had 4.1 to 4.2. I think we lost the big part of that, and we got some money for that too, which I guess helps. Yeah, typically satellite systems, they'll only operate. We only have the luxury of maybe a 10 dB carrier to noise ratio, pretty large bandwidth. This is probably dated by now. We have maybe a 36 megahertz bandwidth. Terrestrial, we have usually a better carrier to noise ratio of about 30 dB, but the bandwidth is somewhat more limited. So these are interesting antennas too. We'll talk about those. These are shrouded parabolic reflectors, and you compare this to a lot of the grid pack antennas that we use for SDL, and there's a pretty big difference in the far outside lobe envelope. Well, I think I've got a slide that talks about this in some detail. And VSoft has some great software. I was reading an article at lunch about some of their new software that they've got for the new proposed FM allocations. I think it's what, C10, I think it is, they were talking about. So you can actually look at that. This is something we typically do. We look at the licensed transmitters all around the site to see what may be a potential interferer. Now, of course, some of these they go on the air without licenses too, but you can actually go on the FCC website for free and get a lot of information of all the licensed emitters around your area. So this is pretty important to do. Been trying to get them to buy the VSoft software, but I haven't quite got them to do that yet. We also use a company called ComSearch. I think there's 2 or 3 others that will also do this. We use a pretty regular basis. Let's talk about antenna noise temperature a little bit. This is probably the first brick in trying to create a good signal to noise ratio with a satellite type antenna or terrestrial antenna. All antennas have a certain amount of noise power that they bring in. You can take a power meter and hook it up to the aperture of the antenna, and it will generate some power. This is a good chart that one of my coworkers did several years ago that shows the antenna noise temperature for different elevation angles over different frequencies. So you can see as you get down here, 200 megahertz and below, it goes up really, really quick. And this is assuming that you're not looking at the ground. I believe this assumes that the main beam is off the ground, but this is 30 degrees elevation. I guess this is on the ground here at 0, but you can see that when you get up here at S-band, you're getting down to some pretty low levels. You're getting down to 30 Kelvin, and the low noise amplifiers that we're using this region now are so good. They're certainly less than 30 Kelvin now too. So we've got receive theoretical receive subsystem temperatures that are what the radio astronomy people were using a few years ago. Just even almost cryogenically cooling stuff now. So we've got some great products. They've made some big inroads up at Ka band recently. We're buying some LMBs that I think they're in the 80, 90 Kelvin. Just 3-4 years ago, they were 120, 130 Kelvin region. So we'll talk about how you look at the G over T or the carrier to noise ratio. But this is the first thing, and it varies with frequency, and it varies with high up above what your elevation lookup angle is. And this chart is really come in handy. I always use this as a first test, and then we have software that will actually calculate this a lot more exactly too. But knowing the antenna noise temperature, what your limitations are, you can see this is 900 megahertz that we use for our STL band typically. Here's just a rough G over T calculation. It's very similar to carrier to noise ratio, and the antenna. What you're doing is you're comparing this ratio of the gain and the system noise temperature at a common point. And it doesn't have to be, but we typically use the input of the low noise amplifier. So the antenna has a certain gain, 32 dBi, maybe a dB of loss before the LNA. So this is going to have like 31 dB of gain for the antenna. So that's the G. And then you divide it by the subsystem, received subsystem temperature. And from that previous chart, a common S-band antenna noise temperature might be 60 Kelvin. But this noise power, like I said, you can hook this up to a noise power meter, and you can actually measure the power coming off of this. It's going to be reduced by whatever this pre-LNA loss is. So basically, you take the power ratio of this 1 dB, and that's where this 1.25 comes. So anyway, you just make a cascade, and anything to the left of this point is going to be divided by this 1.25 LNA loss right here. This is an LNA that has a low noise amplifier that has about 120 Kelvin temperature. Now, the good news is once we get to the right of this gain of the LNA of about 40 dB is going to really reduce the effects of everything after that. 40 dB gain is a power gain of about 10,000. So you wind up with some significant losses, maybe 20 dB of loss, but it's divided by 10,000, the LNA gain. So it doesn't affect it a whole heck of a lot. And you wind up with a temperature, received subsystem temperature, in this case of about 239 Kelvin. So basically, if you just take the gain and subtract off the noise temperature, that's the G over T. And this is a big deal because all received subsystems have a G over T, and this is what you really need to know from a system standpoint to close your link with a certain bit error rate. So I don't do that a lot. I have to generate the G over T, and this is the #1 specification for received subsystems, maybe outside of radar, but this is a big deal. I'll have this spec first. So, and it's really important for any of us if you're trying to put in a point-to-point link. Of course, we have some nice software to do this also too. I just showed a rudimentary example. It'll take into account the energy from the transmitter. We've got white noise, and then we'll go into a diplexer. This is what I was talking about at this point right here. After the high power amplifier, if you've got any cable break right here and it radiates, it's going to bypass this diplexer, which gives you 100 dB rejection. It's going to come right into the received subsystem. So that's what has happened a couple of times with this system up near the Arctic Circle. But anyway, we have software, and we do this every day. So this one has a G over T, a computed G over T of about 19 dB. It's called 19 dB per Kelvin, 19 dBK. So that was our spec. We had about a dB of margin in this particular case. This is a pretty simple, small antenna. Yeah, this is something I want to talk a little bit about too. If you've got a high power transmitter, and you're doing a duplex operation, you know, up and down, you really need to make sure that the white noise power coming out of your high power amplifier is going to be below the thermal noise power of the receive subsystem. And like I said, that it's a big deal now because these LNAs are really, really good. They may be 25 Kelvin. So you can start to degrade your receive subsystem pretty quickly if you don't pay attention to this, or if you have a break like we were talking about. So basically, the HPA outputs a high power, you know, maybe 500 watts, 1,000 watts, and it goes through basically a low pass filter to take out the white noise, because all of these high power amplifiers have a certain amount of white noise, and you got to keep that below the thermal noise limit. You know, it's Boltzmann's constant is what it is. So you can kind of see what the white noise power is in dBW per hertz, and you really want to keep that down to, you know, just a few Kelvin. This will degrade the receive subsystem by this amount. So this is something that is really important, because I've seen people neglect this in the past, usually young engineers, and I haven't seen this happen in a long time, but you know, then they start to stage the thing, and then they turn the transmitter on, and then the G over T is completely, you know, washed away, and it's because, you know, they didn't pay attention to this filtering that we need to have. So you can see in this case, the transmitter, the spec on it was 160 dBW per hertz, and all the transmitter vendors will give you this. This is up in the receive band. They'll tell you what the noise power is. The diplexer illuminate isolations was only about 70 dB. So you can see we're down here around the, you know, 230 dBW per hertz level. So we're down here where it doesn't make any difference, less than 1 Kelvin of degradation. This is one thing that's very important for having a good received noise temperature. And this is getting to be more and more critical as to having this is an S-band feed, and trying to have really good filtering before the low noise amplifier. This is one of the low noise amplifiers there. That's kind of a high-end LNA. It actually will has interstage filters to help reject things outside of the band. So this is getting to be a big deal, and especially after this feed, before the post amps, we're having to put in some new filters on a few sites just because of new 5G applications. This is just some of the new LNBs that have been coming up. There's a lot of suppliers for this, but you can see even at KU band, they've got 35 Kelvin now for the noise temperature. So things that we didn't worry about 10 years ago, 15 years ago, it's getting to be a big problem, because nobody wants to pay a lot of money for an earth station. They want to get all the G over T they can possibly get out of it. So this is just, and these are low end products. These are not expensive products. This is more of a high end low noise amplifier, and it'll actually have filtering built inside. They'll go through the first couple of sections of gain stages, and then they'll have internal filtering, and then they'll follow that up with more gain stages after that to typically get, you know, 48, 60 dB of ultimate gain. But the good news of doing this is, if you get a high-end low noise amplifier, you can do a lot of filtering without hurting the G over T, because it goes back to that G over T table that we looked at. You know, you may go through 15, 20 dB of amplification, you go into some filtering, and since you've gone through, say, 20 dB of amplification, well, that's a power ratio of 100. So whatever this noise power is in the filter, it doesn't affect you by a factor of 100 because of the amplification. So there's a lot of tricks you can play like that, but sometimes at a site you may want to consider going to a good low noise amplifier. There's also some post amplifiers. Many systems you don't have enough gain, so you can get these little mini circuit amplifiers now with half a watt, even up to a watt, for just a few $100s now. And the good news is it's really hard to compress these things. I mean, if you can go up to half a watt, you can have a lot of interference and still not compress the amplifier. Because once we start to compress the amplifier, we'll look at a couple of budgets. Once you start to do that, a lot of the modulation formats, if they go out of the nonlinear region, the bit error rate will go up really, really quick. Anyway, I just want to talk about site interference assessment. How do you assess what's going on? And like I said, we'll go out and we'll do a site survey, and we've got some broadband one. This is a 1 to 18 gigahertz dual ridge test antenna, and we've got there's a guy on the internet that sells these little live periodics for $20, $30. They actually work quite well. This is 400 to 1,000 megahertz, and sometimes I've even put a disc on top of the roof with a spectrum analyzer and let it sit there for several hours too. So it's good to try to capture a lot of the background radiation, and a lot of the stuff may not be turned on all of the time. So that's because if somebody turns something on, after you pack up and go home, that can be a problem. And here's okay, this is one we looked at in the back here in Duluth, Georgia recently, 2021. But this is the kind of stuff we're seeing a lot of. I mean, you're seeing lots and lots of high power signals, and you can see that one's minus 30 dBm right there. So I mean, if you don't have adequate filtering, you get all these composite signals going in, and I'll show that. You can easily overload your low noise amplifier. You can overload a post amplifier. You can overload the receiver. So things are going to go south pretty quick when that happens. I was trying to find something. This is a spectral response we took. I forgot where this was taken. I think it was on the East Coast. And you can see this is our receive band right here. It's gotten a lot worse. We've got these signals all the way up to like 2190 megahertz now. And I was trying to find a overlay of a site on the East Coast and one out in the Pacific, about as far away as you can get. And they were almost identical. So this is not something that's peculiar just around here. We're seeing the exact same thing all over the world. It's getting to be a real problem. And what's happening is you get these signals. We have them up to 2190. The 5G is way up here. There's new carriers coming up here, and you get so many signals. If you find something, rusty hinge or something, then you got a diode junction, and then it creates artifacts up here in the the downlink band. So that gets to be a real problem. So you got all of this stuff coming in, and then the intermodulation effects in the 2.2 to 2.3 gigahertz band, for instance, is getting to be a huge, huge problem. Yeah, this was measured background radiation. Here you can see we've got signals on both sides of us right here. And all of these signals, you got so many carriers, they're creating third order intermodulation products in our band. Well, heck, what do you do if you've got intermodulation products in the middle of the band? You can't filter it out because that's where your downlink is. There's other ways to look at this from a statistical standpoint. We can, record this as a how many incidents that we have over time. So it's just another way of looking at this. Typically, the technician will go out, he'll fill out a site survey, and he'll have the test antenna will have a certain amount of gain with some loss. Usually has a simple amplifier, and then he relates this back to the corrective to get us back to dBm. That's what we usually work with. So we can do a filter analysis. And here's a site just across the street. Here, you can see we've got, I think we've got about 50 watts here, and space loss at 500 feet is only about 82 dB So you can wind up with an awful lot of power into this antenna, especially this is a 7 meter, say at 2 gigahertz. You've got about 40 dB of gain. So you can actually damage amplifiers if you start pointing these things at the new 5G towers. You can actually blow out amplifiers. And the same thing goes with your your 900 megahertz antennas too. So you got to be careful what you point at, because this is a larger gain than we would normally have in broadcasting, but you've got to take this into account. And this is just a real simple version of an overload budget that is based on what we were just looking at, around 2 gigahertz. This uses a 10-watt carrier. You're 500 feet away, so you got 82 dB of space loss, that's spreading loss, 42 dB of antenna gain, 80 dB of rejection from the filter before the LNA. So you wind up with about minus 80 dBm at the LNA power input, with the compressions minus 30. So we wind up with pretty good margin in this case, only because of this filter rejection that we've placed right here. So this is a simple one, but it actually gets more complicated than this, because remember, there was lots of carriers that we had to contend with. So the LNA doesn't, or the amplifiers don't really care about a single carrier, because you've got all of these carriers that he recorded coming in, and probably a worst case would be that you take the composite power of all of these. We've gotten into spirited discussions about whether we should take the RSS or just the absolute peak value on this, but it's a random noise. So the conservative thing is just to take the composite power of all of these and assume that they're going into your antenna, your receive subsystem. And let's see, we were talking about the system that had the coax, the transmit uplink. We've got about 57 dBm uplink, 96 dB of rejection. So that gives us about 39 dBm at the LNA power input. The limit's about 30, which this has the interstage compression. So we've got about almost 10 dB of margin. So at 2.1 gigahertz, the LNA has about 18 dB of gain, because it's out of band. It's 2.2 to 2.3. You got some more losses down here, and you can see we go into a post amplifier down here, usually like that mini circuits, for instance. So it looks like we're okay. We've got plenty of compression margin with this, but again, I put a filter right here too. This is a filter to knock down that 2.1 gigahertz. So there's an adage: filter early and filter often. So these are pretty cheap filters that you can get. They don't have to be great. And but so you're going to wind up at the receiver with about minus 37 dBm of power. So the limit on this particular receiver was about minus 30 dBm. So you've only got about 7 dB of compression right here. So this is just to the transmitter leakage. So you can have this power, plus you're also going to have the composite power from all of these radiators. So there's a lot to consider for your receive subsystem: transmit power, leakage, plus all the other carriers that are coming in. Here's some more recent background radiation that we've measured. And like I said, it's getting worse and worse. We're flanked on both sides by high power carriers. We have Sirius XM on one side, and then we've got all the new 5G things on the other side. But let's see. I won't go into this too much. Occasionally, if we have a really bad situation, we might have to put in a limiter, and these are available off the shelf. We have used these a few times in extreme cases. And what happens is if somebody points the antenna to one of these cell sites, this is basically a pin diode, and it shorts, and it protects the receive subsystem from being permanently damaged by pointing at these things too. So there are these high power limiters that you can use. Let's see. Let's talk about remediation. I only got a few more minutes here, but what can we do about this? First thing is spatial rejection. Like I was talking about, a lot of these antennas that we design, you have the main beam and you have side lobes. And we have both the FCC and CCIR side lobe envelope specifications that we have to stay below. And that helps us on receive and transmit because usually the interference isn't coming from where we're exactly pointed. It's off to the side. But you can still get quite a bit of energy coming in from these side lobes and even the back lobe. So I spend a lot of my time doing these analyses where we play with different illuminations and we're trying to achieve a good gain with a low side lobe envelope. There's kind of an art to that more than anything else. And it's really a function of whatever illumination that you select. We can do that by either the feed or the subreflector. Minimize our central blockage and actually having good precise reflecting surfaces, because if the reflecting surface gets irregular, it causes the side lobes out here to increase, and that will also increase the amount of interference that you receive. It raises this level. The goal is to try to keep this as high as possible and this as low as possible. And the trade-off with that is for maximum gain, many times you have to trade off gain for side lobe level. It's kind of an art to that. Again, this is the geosynchronous art that we talked about. We're trying to keep a low side lobe envelope because of interference from other satellites, or it could be a terrestrial site. And this is some of the typical curves that we see right here, and this is a big deal. We have to make sure that all of these antennas meet this mask requirement. In a few cases, there's a little bit of allowance for overage, but not much with a few of the specifications. You can go maybe 3 dB above with 10% of the side lobes, but generally you have to stay within this envelope. And this is this is the angular region off foresight. So this is in dBi. So you have to stay below this level. Again, you can use spatial discrimination. This is an example of a really low side lobe antenna that designed a few years ago, and you can see you get the main beam, the first side lobe, then it drops like a rock down here, 40, 50 dB past the second side lobe. So you've got a very low potential for interference. This is a more traditional. It's just kind of a gradual fall off. One thing I wanted to mention too, if you have one of these high gain antennas, reflector type antennas, if you're in the near field, the pattern doesn't look like this. It can become bifurcated and it becomes fatter, and so you wouldn't want to make your assessment using far field patterns if you're within the near field of the antenna. And a near field is typically 2D squared over lambda. Anything smaller than that, once you get past, this is the diameter of the antenna squared divided by the wavelength. So that's a classical boundary between the far field and the near field. So it's another gotcha that you need to make sure that you take that into account. If your terrestrial interferer, your 5G tower is say 100 meters away, it's not going to look like this. It's going to look like this over here. And there's other type of reflectors that I know we've all seen and loved, like we were talking about, these Andrew antennas. And our company actually used to make the antennas for cable wave. That's how we got started a long time ago, back in the 60s and 70s. This is a shrouded parabolic reflector. I still use these occasionally, but if you take a parabolic reflector and put a shroud around it, you can see you can cut the side lobe envelope down quite a bit. Now this is for a small reflector in terms of wavelengths, but the red is unshrouded. If you take some aluminum and wrap this around, you can really reduce the side lobe level, which helps. And also they put a little radome over the top of it. It has a double purpose. They take the shroud and put the radome over the top of it. So you see these all over the place still. And there was an antenna called a cornucopia. I know everybody remembers seeing these things. They were used in long lines. These are phenomenal. Basically it's an offset reflector, and they use horsehair absorber to try to mitigate a lot of the diffraction effects. And you can see that the front to back ratio is phenomenal. I think that it's close to 100 dB. You guys can probably talk about this better than I can, but these were actually pretty phenomenal when it comes to side lobe, and because that was a pretty big deal in the long lines. They were trying to mitigate uh, interference, and that was you don't see too many of these left. There's not too many terrestrial telephone long lines, but that was actually quite a neat antenna, and you can kind of see the phenomenal side lobe envelope. I've heard of people actually using these. One say one going north, one going south, and I've heard of people actually using them on almost the same frequency, and they use the really high spatial discrimination so they don't even need that much duplexing. You can have almost the same frequency and not set up an oscillation. So that's just what I've heard. I've talked to some long lines guys, and they couldn't really validate that, but you guys may know more about that. There's also other types of antennas. You can use an absorber shield. If you're pointed towards the earth, we talked about antenna noise temperature. If you're pointing towards the earth, like we would do with an STL, you're going to get a 290 Kelvin antenna noise temperature. It's going to set the antenna noise temperature because you're looking at hot earth. As you start to go off of the earth, remember that curve I showed earlier, as you start to lift the antenna in elevation above the earth, then you start to see the big improvements in the antenna noise temperature. So that allows you, if you've got something that's terrestrial, you can do things like use absorber and things like this. If we had one newbie antenna engineer that thought he was going to fix a lot of problems with absorber, and he was using it for a space application, and that just destroyed the antenna noise temperature. So it's not a good idea if you're looking at space, but if you're looking in the for terrestrial, your antenna noise temperature is going to be set by looking at the hot earth. These are some more non-ideal. Probably remember the fly swatter. We used to have these a long time ago. You just have a metal plate up at the top. It's really convenient because you can have a parabolic dish on the ground, and it illuminates this plate up at the top. And if you have to do any work, it's all down here. So they're really convenient. I don't think the FCC's allowed these in quite a long time now, because they spray out a lot of energy all over the place. But it's actually pretty convenient to work on, and everybody's very familiar with a typical mesh grid reflector, 950 megahertz. This is really, really small. This is only maybe 4 wavelengths across at 900 megahertz. So it almost looks like a ground plane as much as it does a parabolic reflector. So you don't get a lot of discrimination off of this. But the good news is they're cheap and lightweight, low wind loading. We do measure a lot of our antennas, especially first article in our antenna range. It's about 25 miles away from where I'm sitting now, up in Pendergrass, Georgia. It was close, and real estate got to be a big deal. This is a 1,500-foot range, so there's a transmitter 1,500 feet away, and then we can record the what the antenna looks like as far as side lobe. You can kind of see the side lobe pattern here. We need to validate that for the FCC compliance and validate the gain. So usually first article testing, we like to do that. I want to touch just briefly on passive intermodulation. We could probably have a whole talk about this, but we spend a lot of time with this. And basically what that is when you have two high power carriers, they mix together in like a diode junction. It's almost like a mixer, just like a mixer, and then you can generate artifacts in your receive band. And there was a case that we all heard about where there was a man, you might have been on here. He got a call from the FCC and said he was interfering with the instrument landing system over at the airport. The FAA called him, and everybody went running out there. And after a week or so of investigation, they found out that the culprit was some rusty hinges on the enclosure for the instrument landing system, the ILS system. So anyway, I thought that was kind of interesting. And usually it's something external, but you got to have high power. It's pretty lossy. Conversion loss is pretty high. So you have to have two high power carriers to do this. It could be inside the antenna or it could be external. If it's external, what do you do? I mean, what we're doing on a couple of cases now is we're having just almost abandon the bottom end of our satellite band because the 5G intermodulation effects are getting to be such a problem. So anyway, I think this is the one I was talking about. I don't know if he's on our site or not, Jeremy Ruck. I know everybody knows him. He had an article in Radio World a few years ago. But it used to be with the FCC that the last N had to fix any type of problems, but I don't know if that's really still the case with the cell carriers. They seem to have a lot of money. Of course, we have our rejection for our trade to contend with, and we have an intermodulation lab here that we do a lot of intermodulation components, and basically we'll actually have waveguide junctions. They'll actually be lapped so they're perfectly smooth. They'll actually hold pressure without any gaskets. That's how mirror finish they are, and that's because anything that has a wavy gap to it like that, you can get micro arcing. Micro arcing will cause intermodulation effects too. So this is something that could really degrade your received subsystem if you have multiple carriers. Anyway, it's and you can tell it's not a one-to-one relationship between the intermodulation carrier and the power that goes into it. It's more of a square relationship. So that's one way you can tell if it's intermodulation. For instance, here's a transmitter at 8 gigahertz and 8.3 gigahertz, and the combination of these, if you just take 2 times one frequency minus 1 times one of the other, it'll start to make these intermodulation products in these frequencies right here. And for instance, this case right here, we had a 8 to 8.3, and then our receive band down here is down here, and then we've got an interference that precludes being able to receive this signal from the satellite. So there's a lot of things to consider with this. We have a intermodulation test lab. We have 2 high power transmitters. They're 1,000-watt transmitters, primarily at X-band. And we'll actually feed it into the antenna. We start with a feed, wind up with the entire antenna structure, and validate that the power that we receive is below a certain level. I mean, it's typically 125, 130 dB below the carrier. It's pretty significant. And this is actually doing some of the tests. We actually took part of the transmitters outside into one of the antennas. It's fairly common. And this is actually where the unit's inside the control building that we have this set up at. So this is something we spend a fair amount of money on. So we have to take this seriously. And this is really a big deal if you've got multiple carriers. If you've got if you're duplexing 2 carriers into one, you can create these intermodulation products that can be in your receive band. So it's something to be aware of too. I'm going through this pretty quick, but this is actually a feed subsystem, and a lot of these are pretty precisely made. A lot of them are electroformed, so they're contiguous. They're not things just bolted together. So they're pretty high end, and even the reflector and some of the components, you don't see a lot of stainless steel. And we had a situation where some of the mechanics, I didn't know it, they used something called Never-Seez on some of these bolts to put the thing together. Never-Seez has metal particles in it. That was acting as a diode. And my co-worker Fred here, I don't know how he ever found that, but he did. And stuff like that will just about drive you crazy. And also, we've also had passive harmonic, like with flight termination systems. This is some systems that we did where we were transmitting in the UHF band, and then receiving maybe on the 4th or 5th harmonic up in S-band. And we had the same kind of thing. We had to make this so that we had no diode noise junctions. Even if you have a single carrier, if you're on a harmonic, called a passive harmonic, this can be a interference problem too. And you have to go through exactly the same steps. You really want to avoid stainless steel. You want to avoid gaps, like we showed, that needs to be continuous. So anything that creates a diode, you don't want that. That's what you have to almost think about. In fact, what we use as a calibration is we take a diode, put it on the end of a wooden stick, and you can make sure that the system's working. I won't spend a lot of time with this. I know we're just about out of time, but we've got a lot of systems that we've dealt with over the years, and we go through, we add up all of these different carriers and put them together. We want to make sure that we have enough margin. If you want to get a good discussion with the systems folks, you just ask them what's enough margin, and most of them will agree 10 dB is adequate margin to keep you out of compression effects. But you can say we only had about 5 dB in this particular case. And we're doing, unfortunately, we're having to replace some filters in some cases with their sharper filters. Good news is there's some high-end filter vendors that can really do some miracles now. Their techniques have improved a lot in the past 10 years. So we're able to get really steep skirts and pretty phenomenal performance now. But these aren't your mini circuit filters. These are a bit higher end filters that we typically put in there. And we've been doing this, unfortunately, I hate to say it, we've been doing this a fair amount. As older systems and people put in 5G and we start to get all these interferers, you can try to eliminate a lot of this with sharper filters. And what you can't do is, if they're creating intermodulation in the passband, for instance, say right here, you can't do anything about that. The only thing you can do is either cut this out, or you try to fix the source of the intermodulation, which is, the rusty hinge syndrome that we talked about. And this is one of my former co-workers here, and you can see we've got a good post amplifier here, a really good diplexer. This is a 1,000-watt coax diplexer, and we've got another filter right here these are pretty inexpensive. Once you get past the low noise amplifier, you can use cheaper components. You don't have to use super high-end components because loss and performance is a lot less critical because of the G/T. This is another post amplifier assembly. This is a mini circuits filter. They're fine for what they are. They're $30 off the shelf, and we replaced it with this filter here that we got from one of our vendors. And you can see the slope is a lot better. And you can see the amplifiers. I think the amplifiers are, these are the old filters, and then these are the amplifiers right here. This is an amplifier. This is a box that's after the initial amplification. So, but we're having to do a fair amount of filter replacing now. Oh, this is another thing too. I've had to do a diffraction fence even to protect against a TV ENG repeater. This is in the shared band. Thought this was kind of interesting. People thought we were a drive-in theater, but you can see it actually worked really well. Any energy that goes towards the 2,000-foot tower, which is about 10 miles away, is pretty much diffracted off of this diffraction fence right here. So it actually worked out pretty well. So sometimes you have to actually do things like this to mitigate reflections. So I did some tests, before and after we built this, and I got to climb the 2,000-foot tower. That was kind of fun. So always looking for an excuse to do that. That's about it. Conclusion is, there's a lot of things to consider when you're on a shared site. Using high compression LNAs, not necessarily getting the cheapest LNAs, goes a long way. And you need to really determine with a site survey what your signal level is coming into all of your amplifiers, the LNA, the post amplifiers, your receiver. And if you can, use lockout zones from the antenna. We've had to do that a few times too. If you have a high power radiator and you just don't point the antenna in that direction. Sometimes the implementation of that is not trivial because you have to make sure that whatever you're wanting to see is not in that direction. We've talked about updating filters. There's good news is there's a lot of really good filters out now. Top filter vendors, they can really pull a rabbit out of their hat now a lot of times. I usually try to get, I've got one that I really like. I'd consider him to be one of the top 1% filter designers in the world. So we use him quite a bit. He probably does 99% of our stuff. And anyway, don't forget, if you are close to a site, like a 5G site, you're not going to get the spatial discrimination that you would expect in the far field and the near field. It's going to be, you're going to have less because the pattern gets fatter. And it's a regular thing for us to have to calculate these near field patterns and show what kind of discrimination we can expect. And don't forget spatial intermodulation. If you've got, passive intermodulation, if you've got multiple carriers, high power carriers, you can generate intermodulation products in your receive band. Just anything that can act like a diode mixer. It could be a rough surface. It could be where two pieces of metal don't necessarily mate very well. Like I said, these low intermodulation systems, we actually lap the waveguide flanges, so they're a mirror finish. So there's a lot of things that you can go through. That's about it. Appreciate your attention. I'll be glad to talk about whatever I can. This is just kind of a side thing I've been doing. I primarily I do antenna design, but we've been getting a lot of discussion, help from the field recently with upgrades and things like this.
Ray?
Yeah.
Pierre would like to know where you can get those filters you just talked about.
My favorite vendor, the coaxial filter, is a place called Microtronics. Ask for Mark at Microtronics. He stays pretty busy, but like I said, I think he's probably one of the 1%, the best coaxial filter designers in the world. I mean, he's. I mean, you can pay, you talk about hundreds of dollars for filters instead of $30 a filter, $40 a filter. But he's excellent.
Roland says years ago, I met with an AT&T field tech who complained about the co-located LPFM out-of-band emissions that he sees at the output of his AT&T mobile antenna. I showed him the LPFM is compliant with the FCC regs, so there's really no need for the LPFM to install additional filters. Never heard back from AT&T, but his question is there a case study, white paper, or any documentation you know of that I can get that can show the burden of mitigation is not on the LPFM only, since it is FCC compliant. The low noise floor required by the cellular company is the one that needs some work on their dime. I just figured that similar case explained in writing will we put the issue to rest or maybe not.
Well, Barry, you probably know a lot more about that than I do. I mean, what if we've got the 70 dB, the mask that from our spectral emissions from our FM transmitters? I can't recall it off the top of my head right now, but
used to be a big problem with LTE there. The seventh or eighth harmonic was landing around the LTE, and AT&T got a really nasty reputation of coming in and telling stations, "You better fix this." And because of them being so big and the station maybe not so big, but it was a real problem for quite a while. There's a couple of articles, one by Gary Cavell on the BDR here, talking about this problem and how it could be as simple as needing a Faraday cage or checking the finger stock on the doors of an exciter.
Was he the one that talked about the inquiry with the FAA? The FAA said there's been a couple of interesting stories, but the FAA said the ILS was down. And if you want to get the FCC's attention, just tell them it's a hazard to radio navigation. So
Yeah.
they came out and they found out the culprit was actually the enclosure that the ILS transmitter was at the end of the end of the runway. And of course, they had several FM broadcast stations around the airport. So,
Now you are ViaSat, and there are two questions that come up. One, which I think Pierre was involved in, where Viasat is blocking certain URLs, especially for people up in Alaska. Do you know anything about that? Anything different than what we heard last time?
yeah, I sent an internal inquiry in, and I think Michelle was part of that too. And there was some discussion about the carrier that I mean the internet service that they were using. Apparently, I don't know. Some people thought it may not be the best. I'm not the one to expert, but I actually input a internal request. I haven't heard back from it, which is I need to check on that.
It was
But,
Michelle's site that was being blocked up in Alaska there.
well, yeah, and I validated the same thing. I have the Viasat at home, and I saw that, and I told them I thought this was a good site. But you know what's interesting is at work I can see it just fine.
Mhm.
And I don't know. A lot of times, what they'll do is, if you can tell them that this is a good site, they'll let it through. But I'll check tonight at home. I haven't checked since
Okay.
that, but a
Let
lot of
me
times
ask
let them know.
let me ask this question then. As Viasat, if somebody is finding interference on their STL or their main channel, do you often go out and help a radio station with your spectrum analyzer?
No, I've never done that. It's all the closest I've done is we did the Earth station that was in direct line of sight of the 2,000-foot tower, and we had to prove that we were below the limit for that. I wouldn't mind doing that, but no, we don't get calls generally from terrestrial radio stations like
Mhm.
that. Uh,
The problem with the LTE especially was that ANTT wanted something like minus 120 at their site there, and that's just almost impossible uh, if you have a transmitter that's running 50 feet away.
yeah, I
Anyone
was
have any questions for Ray? Uh, I can't be the only one here that's got questions. Very interesting discussion. I think you'll all agree, and we'd like to know more about what happens if you're up on a shared site and something you need to know about.
it's pretty complicated. This is a lot of material, and I just tried to do an overview of all the things you have to consider when you're putting in a site. And if it's intermodulation effects, if it's overload's a big deal too. I mean, you got two big things. You got overload, intermodulation effects. If you can stay away from that, because these digital systems don't like it, QPSK when you start getting into compression, a lot of them. So
Have you had any Starlink issues?
um, no, I've never played with Starlink. I've never, I've never. We've got the Viasat, but which is geosynchronous, by the way. But no, nobody's. I've got some coworkers that went to work for Starlink, but that's about it. See them occasionally at the some of the antenna shows, symposiums.
Any other questions for Ray about satellite reception, harmonic interference, or anything else about being up on a shared site? Maybe he knows, maybe he doesn't. I know that in LA at one point, the FCC came in and I think it was, now one of you guys can maybe tell me, I think it was that they cited everybody because there was too much RF on the ground.
You mean from an RF safety standpoint?
Yep.
Okay, that's a big deal too. Um, And we typically have to do RF safety analyses now for just about all of our systems now.
That goes to the last one in situation that you may be having a good site, but somebody comes in and pushes it all over.
Well, I mean, yeah, they're worried about exposure, especially, I mean, if you get multiple kilowatts into a 60 dB gain antenna, that's a lot of power.
Mhm.
So,
Ray, I wanted to say hello. This is Mark. I worked at Scientific Atlanta between 88 and 95. I don't think we ever crossed paths. I was in sales network systems there on Beaver Ruin. And I know that was all bought out by ViaSat. And
Yeah.
very good on that Fox Tower up by the lake. What was the reason again you had to certify that tall tower?
well, the electronic news gathering repeater is a shared frequency with the S-band uplink 2025 to 2120. They're and I think we're secondary basis, or at least that, you know, maybe they were incumbents. So we had to prove to them, and that's my old employer too, by the way, too. So, but we just had to prove that, you know, there was no effect. And we put up that big diffraction fence and worked really well. So probably overkill. People around there thought they were getting a new drive-in movie theater. So thought that was kind of funny. Don't see too many of those anymore. But yeah, that's kind of an extreme example of something you might have to do to mitigate interference.
And that can even be down on the ground floor. You don't have to be on a shared site necessarily. If you have a satellite receive point, you have to be careful about a lot of these things too.
Yeah, it's getting there. Yeah, cabinet radiation is it's important too. Yeah,
Yep.
so.
Okay. Ray, thank you so much for a very nice program. We appreciate it.
I've learned an awful lot from you guys. I really appreciate it. So got a lot of just I'd hate to add up all the years of experience we have on this in this group right now.
At least
It'd be
3 or
a lot.
4.
Yeah.